Pluto is a remote and puzzling smaller planet that was once a piece of our sun-powered system's planetary gathering. However, later astonishing declarations by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a surprising revelation. They recommended that this cold world is on a potential impact trajectory with Neptune. Yet how is it that this could happen, and what might be the repercussions of such a giant event? Are we seeing an intriguing galactic phenomenon, or is there something else to this approaching infinite conflict? Join us as we explore the potential outcomes of a Pluto-Neptune influence. Pluto, a former planet that was renamed as a dwarf planet in part because of its surprising orbit, remains a subject of interest and exploration in the galactic community. According to late figures by leading researchers, Pluto's orbit is perilously close to Neptune's, with both Neil deGrasse Tyson and Michio Kaku sounding the alarm about a potential risky crash between these two planets that could present a critical danger to Earth. How is such an event even conceivable? Pluto's orbit around the Sun is dissimilar to any other planet in our nearby planetary group. It requires a surprising 248 years to complete a solitary orbit. Since its discovery in 1930, it hasn't indeed completed one full revolution. Be that as it may, the interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, diverging remarkably from the nearly circular orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination, calculated at 17 degrees to the ecliptic plane. The way Pluto follows is much more extreme compared to other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most interesting aspects of Pluto's orbit is its crossing point with Neptune's path. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, challenging what we may anticipate from their positions in the solar system. This prompts the regular question: why hasn't Pluto slammed into Neptune? The answer lies in the gravitational impacts of other planets. The investigation of Pluto's orbit began soon after its discovery. At first, cosmologists attempted to grasp its unusual path. Unlike the other planets, whose orbits lie somewhat near the ecliptic plane, Pluto's path stood apart with its steep inclination and elongated shape. The mystery grew with the acknowledgement that Pluto's orbit indeed intersects Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricate design of space mechanics. The three-body problem in space involves figuring out how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like attempting to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how the orbits of Neptune and the Sun's gravity all interact in a complex manner. The terms OL libration and scope libration, along with VZK oscillation, are part of this riddle, as indicated by astrophysicists. What's keeping all planets in their orbits is AU libration. In the specific context of Pluto and Neptune, this term implies that whenever Pluto crosses Neptune's orbit, it's situated something like 90 degrees away from Neptune. This spatial separation is crucial in keeping their paths from colliding. Scope libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it comes nearest to Neptune or some other giant planet, it's positioned entirely above their orbital plane, providing an extra layer of protection from potential impacts. Another significant part of this equation is the VK oscillation, named after three researchers, von Zeipel, Kappas, and LV, who studied how objects move in space. It describes how three celestial objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This pulling influences how they move, and in Pluto's case, the VZK oscillation helps us understand why its orbit around the Sun is so unusual. Despite its seemingly chaotic path, Pluto's orbit remains stable for an incredibly long time, like billions of years. This means Pluto's journey around the Sun has a sort of order to it, even if it appears erratic at first. Predicting infinite events, especially when they involve turbulent orbits like Pluto's, poses critical challenges. The intrinsic unpredictability of these systems implies that long-term forecasts are often filled with uncertainties. While numerical simulations provide a robust means to understand and predict the future paths of celestial bodies, they also highlight the limits of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any minor mistake or misrepresentation can lead to vastly different outcomes, making accurate predictions an overwhelming task. Moreover, the tumultuous nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto serves as a reminder that our knowledge about the universe still remains limited. Understanding the gravitational impacts of the giant planets on Pluto's orbit provides significant insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have widespread effects on the stability and paths of different bodies within the system. So why are prominent astrophysicists just now raising concerns about a possible impact between Pluto and Neptune, despite all these forces working to prevent such an event from occurring? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in promoting cosmology, offers a unique perspective on the mysteries of our nearby planetary system, especially the intriguing case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, provides insightful discourse on the evolving nature of celestial mechanics and the public's interest in the unexplored realms of space. Tyson's position on Pluto's renaming is grounded in the continually expanding knowledge of our solar system. He sees the renaming not as a downgrade, but rather as an important adjustment to our growing understanding of the many bodies orbiting our sun. Tyson's approach to celestial mechanics is one of ongoing learning and adaptation. He views the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The interest in these questions, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and unpredictable nature of our nearby planetary system. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another esteemed physicist and futurist, offers a different yet complementary viewpoint on the mysteries of space, focusing on the often chaotic forces that shape our universe. Kaku is known for his ability to connect complex scientific concepts with visionary ideas, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's perspectives on Pluto and its orbit stress the need for continuous observation and advanced modeling to anticipate and understand potential cosmic events. He sees the interactions between celestial bodies as an important area of study, not only for academic interest but for practical implications. The potential crash between Pluto and Neptune, for example, is not just a hypothetical scenario but a reflection of the dynamic and often turbulent nature of space. Kaku's futurist perspective urges us to consider the broader ramifications of such events, from their impact on our understanding of the solar system to the potential need for future space interventions. His viewpoint underscores the importance of being prepared for the unforeseen in space. Kaku suggests that the more we comprehend the forces at play, the better equipped we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku's perspectives converge on the idea that space is a realm of infinite discovery and that our current understanding, while vast, is still limited. Their emphasis on the need for ongoing exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not just understanding celestial mechanics as they are now, but also anticipating how they might change in the future. The potential collision scenario between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It emphasizes the need for robust scientific inquiry, advanced technology, and a willingness to adjust our understanding as new information arises. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to continue pushing the boundaries of our knowledge. There is a general scientific consensus that, for the foreseeable future, the orbits of Pluto and Neptune remain stable due to their mean motion resonance and the various gravitational influences acting on them. Consequently, a direct impact between Pluto and Neptune is highly unlikely. However, the complexities and potential perturbations in orbital elements mean that astronomers should continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they may present. While the prospect of a Pluto-Neptune impact is largely speculative and considered improbable with current understanding, it underscores the importance of continuous research and observation in space science. Advances in technology, including more advanced telescopes and virtual simulations, will assist astronomers in refining their models and predictions, ensuring that we remain informed about the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the unpredictable nature of celestial mechanics both highlight the necessity for ongoing exploration and a flexible understanding of our universe. The potential impact scenario, while underscoring the dynamic and complex interactions within our nearby planetary system, ultimately reminds us of the vast, still unknown realms in our understanding of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving universe. Pluto's status as a dwarf planet has sparked ongoing debates within the scientific community and beyond. The criteria established by the International Astronomical Union, IAU, for classifying celestial bodies led to Pluto's reclassification in 2006. This decision was not just a matter of semantics. It reflected a broader understanding of the diversity of objects in our solar system. Many astronomers believe that such classifications may evolve further as we discover more about trans-Neptunian objects and other celestial entities beyond Pluto. The dynamics of the Kuiper Belt, where Pluto resides, are fascinating in their own right. This region is filled with icy bodies and remnants from the solar system's formation, providing insight into the early conditions of planetary development. Pluto itself serves as a unique laboratory for studying these primordial processes. Its complex atmosphere, consisting mainly of nitrogen, methane, and carbon monoxide, undergoes seasonal changes that intrigue researchers. As Pluto moves closer to the Sun during its long orbit, its surface temperature rises, causing the ices to sublimate and contribute to a thin atmosphere. This cyclic process highlights the intricate interactions between celestial bodies and their environments. Additionally, recent discoveries made by spacecraft like NASA's New Horizons have revolutionized our understanding of Pluto. The 2015 flyby offered unprecedented images and data, revealing a geologically active world with mountains, plains, and possible cryovolcanoes. These findings challenge previous assumptions about the planet's inertness and have opened new avenues for research. They suggest that Pluto might harbor a subsurface ocean, further complicating its classification and importance in the study of icy worlds. In considering potential interactions with Neptune, it's essential to examine the broader gravitational landscape. The influence of other celestial bodies, such as the larger gas giants, Jupiter and Saturn, also plays a role in shaping orbits. Their massive gravitational forces can create perturbations that ripple through the solar system. Understanding these gravitational interactions provides context for the stability and evolution of Pluto's orbit over eons. Astrophysicists utilize various observational techniques and simulations to study the potential long-term impacts of these gravitational interactions. Advanced modeling, which incorporates both observational data and theoretical physics, allows scientists to predict future behaviors of celestial bodies more accurately. The complexities of these models underscore the importance of computational power and algorithmic advancements in modern astrophysics. Moreover, the public's fascination with Pluto and its dynamic nature reflects a growing interest in planetary science. Popular science media, educational outreach, and community engagement initiatives have helped spark curiosity about the cosmos. Events like Pluto's Discovery Anniversary and missions to distant worlds have galvanized interest in space exploration, encouraging young minds to consider careers in science and technology. Looking ahead, the possibility of future missions to explore Pluto or similar bodies in the Kuiper Belt could yield transformative insights. Proposals for new spacecraft are already under discussion, aiming to investigate not only Pluto, but also other intriguing objects in its vicinity. These missions could provide data that challenges existing models and enrich our understanding of the solar system's formation and evolution. In summary, Pluto's journey through our collective understanding exemplifies the dynamic interplay of discovery, classification, and exploration. As we continue to unlock the mysteries of this distant world, the collaboration between theoretical astrophysics and observational astronomy will play a crucial role in shaping our knowledge of the universe. Each new revelation invites further questions, propelling the quest for understanding beyond the familiar boundaries of our solar system.